Hi, so today's presentation is going to be on interference. So before we start with the new material, I just want to do a little bit of revision on some National 5 subjects that you need to remember for this. So just a little bit on wavelength of a wave. So just a little reminder that wavelength is the horizontal distance between two similar points in a wave, and it's measured in meters. So the wavelength can be from like crest to the next crest. It could be from one point to the next point in a wave. You can tell which points you need to look at because the wave then starts to repeat itself. So you can see that from here it goes down, up and down again, then it goes down, up and down again, so it starts to repeat itself, okay? Or from the trough to the next trough. Then the amplitude is the distance between the rest point in a wave and the crest, or the rest point and the trough, and it's also measured in meters. A couple of formulas that you need to be remembering as well. First one being F is equal to N divided by T, F being frequency, so frequency is equal to the number of waves passing a point divided by the time it takes for those waves to pass that point. Frequency measured in hertz and time obviously measured in seconds. And then the period formula, so period T is the time it takes for one wave to pass a point and is measured in seconds. And if you know frequency, you automatically know the period because they have an inverse relationship, which means that T is equal to 1 divided by F. Okay, so if you just want to pause here and have a little go at these questions. Okay, and just mark them as well. Those are the answers for you. Okay, on to the first new thing. So phase of a wave is the measure of how in phase the waves are, how in step the waves are. So this picture shows two waves that are exactly and completely in phase. The waves match up perfectly. The crest here matches up perfectly with the crest there. The trough here matches perfectly up with the trough here. And it doesn't matter how far along the wave you go, it's always going to be crest matching up with crest, etc. Okay, so these are completely in phase. Something that's completely out of phase would be something like this. So you can see that the crest of the first wave is meeting with the trough of the second wave, and then the crest of the second wave is meeting up with the trough of the first wave. Okay, this is what is said to be completely out of phase. Now, if you have two waves that are meeting in phase, these two waves are meeting in phase because their crests match up and their troughs match up, okay? They combine, they just kind of like add together, okay? And they make a wave that has, you can think of it as like double the amplitude, okay? The same wavelength as the original waves, but double the amplitude, okay? And when this happens, when two waves combine together like this, when they're in phase, it's called constructive interference, okay? And we'll discuss what that actually looks like and what that sounds like in a second. Yes, I do expect you to try and draw these into your jotter. Good luck with that. And this is what is known as destructive interference when your waves match up out of phase. So we can see that they're out of phase here. We have a crest matching up with a trough and a trough matching up with a crest. When they add together, they just cancel out. So it's called destructive interference because the waves are just kind of, well, they're destructing themselves. They're no longer there. They cancel each other out. Now, this is an important wee note down here. Constructive interference or total constructive interference and total destructive interference will only happen if the waves are coherent. Now, what coherent means is when the phase difference between waves is constant. More or less, the waves are the same as each other. Okay, they have the same amplitude, they have the same wavelength, they have the same frequency, etc. Okay, so the waves do need to be coherent. Right, so obviously we can't do this, but I'll just kind of explain what we would see from this experiment. So usually I set up two speakers that are attached to the same signal generator. So they are producing the same sound. They're producing coherent sounds, okay? And what we do is we just walk up and down the classroom. And what you should hear are spots of loud sounds and then spots of quiet sounds. Now, when you hear a loud sound, you can say that constructive interference is happening because the two waves from the two speakers are adding together, their amplitudes are adding together, therefore they're creating a sound with a higher amplitude, therefore it's louder, they're meeting in phase, constructive interference is happening, loud sound is created. When you hear a quiet sound, that is means that destructive interference is happening. The waves are meeting out of phase, destructive interference is happening, and therefore you can hear just a quiet sound. If this was a perfect experiment in the perfect physics world, obviously the sound would cancel out completely, but just due to like echoes and things like that, it doesn't cancel out completely, but you do hear a quieter sound. And that's because destructive interference is happening. You can also see this with light, because obviously light is also a wave. So what we usually do is we get a laser and we shine it through a double slit. So what it does is it just takes the laser light and just splits it into two. So the light coming out of these two slits is exactly the same. They are coherent. And we shine it on a screen. And what we see is this sort of weird pattern here, that we see bright spots, and the bright spots are where constructive interference is happening. The waves are arriving in phase, therefore adding themselves together, creating a bright spot. And then there are points where there is no light at all, and that's when destructive interference is happening. The waves are arriving out of phase. Okay, so therefore it is a dark spot. So it happens with light and sound. You don't need to draw this in, don't worry. Now, this phenomena, interference, it can only be explained by waves. Okay, if interference is happening, it's because the thing that you're looking at is a wave. Therefore, interference experiments can be used to prove that light behaves as a wave. Now this will come into the course again, because in a few topics time we actually prove that light behaves as a particle, and that opens up a few questions, but this experiment proves that light behaves as a wave. Okay, and that's a really, really important thing in physics as a whole. Okay, path difference. Okay, so this is the sort of maths behind this little topic. Okay, so let's just sort of read through this. Okay, imagine we have a setup below. We have speaker 1 and speaker 2. We'll just talk about sound at the moment. And where these dots are, okay, so m is equal to 1, 0, 1, 2, we have constructive interference at these points. Okay, now if we were to look at this setup, okay, and we were standing at m is equal to 0, we were standing directly in the middle between speaker 1 and speaker 2. Is there any difference between the distances that the two waves have travelled? Well, no, because if you joined up a line between, say, speaker 1 and speaker 2, you'd have an isosceles triangle. Okay, the distance between speaker 1 and m is equal to 0, and the distance between speaker 2 and m is equal to 0 is the same. Therefore, okay, so I'm looking at the bottom paragraph now. Therefore, the waves from S1 and S2 travel the same distance, sorry. So we say that the path difference is 0, okay? The paths taken by the waves coming from speaker 1 and the path taken from the waves from speaker 2 is the same. So the difference in those paths is 0, okay? When they meet at m is equal to 0, it creates constructive interference, okay? So we've got a loud sound at m is equal to 1, okay? And we call this point, m is equal to 0, 0 order maximum, okay? It is the first point where we hear a loud sound, okay? So we call it the 0 order maximum because there is 0 path difference. Okay. Oh, I should say I do want you to draw these into your jotter. Okay, I usually do give you handouts, but I am going to have to get you to draw these in. Okay, apologies. Okay, so next one we are going to look at is here. Okay, so we now are standing, we can imagine we're standing at m is equal to 1, this point, okay? S1 and S2 are meeting to create constructive interference, okay, so the waves must be in phase. I'm telling you that this point we have constructive interference, okay, so we're hearing a loud sound. So therefore, if we're hearing a loud sound, we know that the waves must be in phase, okay? If they're in phase, we're hearing a loud sound. But this time there is a difference in the distances travelled. You can see it here. Okay, the distance travelled from for the waves from speaker 1 is less than the distance travelled by the waves from speaker 2. We can just see that that line is shorter than that line. So we do have a difference in path difference, or sorry, we have a difference in their paths. So therefore, we know that there must be a path difference, and turns out at m is equal to 1, our path difference is equal to the wavelength of the waves. Okay, so if we were standing at m is equal to 0, we hear a loud sound, then we start walking slowly. M is equal to 1 is the first time that we hear a loud sound again. Okay, so therefore we call it the first order maximum because the path difference is 1 wavelength. Okay, yeah, so now we are going to be looking at this one. So we are now, we were at m is equal to 1, then we move slowly until we hear the next loud sound. Okay, the next loud sound is at m is equal to 2. We hear a loud sound, therefore we know it must be in phase, but this time the path difference is equal to 2 lambda, or 2 multiplied by the wavelength, and therefore it's called the second order maximum, okay, because the path difference is 2 lambda. Exactly the same happens if you were moving this way, okay, so if you hear a loud sound here, that is still the first order maximum, okay, and this is still the second order maximum, okay. There are loud sounds either side of the 0 order maximum, okay, and this continues on, okay. M is equal to 3 will be the third order maximum, M is equal to 4 would be the fourth order maximum, etc., etc. Okay, so in these examples, we are going to be looking at when they are meeting in between the maximums. Okay, so if we are hearing a maximum sound here, a constructive interference, a loud sound, and then we walk here, we'll hear a quiet sound. Now, if we hear a quiet sound, we know that the waves must be arriving out of phase, therefore constructive interference happens. We don't call this a maximum, we call this a minimum or a minima. At the first minima that we hear, okay, we call that the first order minimum, and the path difference at this point is a half of a wavelength. Now, I mentioned this before in the presentation. I will film another little bit on how we kind of get to that stage, how we know that it's half a wavelength. I will film a little bit on that later. I just can't do it on PowerPoint, unfortunately, but I will upload another wee video going over that. Anyway, we call this the first order minimum because it is the first minimum we get to. Now, it's important, this will be important later on when we look at the equations that are associated with this, that when you're looking at the first order minimum, you sub in m is equal to 0. Now, as I said, this will become important in a second. So, last little thing, the path difference when we are standing here. Now, we hear a loud sound here, a quiet sound here, a loud sound here, so it's going to be a quiet sound here. It's a point of destructive interference. The waves are arriving out of phase. This is called the second order minimum because it's the second minimum you would get to if you were walking this way. Exactly the same would happen if you were walking this way. Okay, and the path difference here is found to be 1.5 wavelengths or 3/2 wavelengths. As I said, I will go over how we work that out in another video. Okay, equations. So for a maximum, the path difference is equal to the order of maximum multiplied by the wavelength, so relatively easy there. If you're standing at the first order maximum, you'd sub in m is equal to 1. If you're standing at the third order maximum, you would sub in m is equal to 3. If you're standing at the fourth order maximum, you would sub in m is equal to 4. For a minimum, the path difference is equal to m plus a half times wavelength. Now, this is where it gets a little bit annoying. Okay, for a minimum, if you're standing at the first order minimum, you sub in m is equal to 0. If you're standing at the second order minimum, you sub in m is equal to 1. If you're standing at the third order minimum, you sub in m is equal to 2. Okay, because at the first order minimum, as discussed, your path difference is half of a wavelength, therefore your first order minimum m has to equal 0. At the second order minimum, we discussed that the path difference is 1.5 wavelengths, therefore you have to sub in 1 here. It's quite annoying, I know, but you are mostly asked about maximums, not minimums, so yeah, you can take that. Yeah, path difference is measured in meters. Order of maximum doesn't have a unit, and wavelength is obviously measured in meters as well. Right, so for a wee worked example, if we're wanting to calculate the wavelength of the waves, if point x here is the third order maximum. So our path difference we can work out because it tells us how far or what distance the waves are travelling from this point to here and this point to here. So we just need to find the difference in these two values, which is 12 centimetres. You just need to remember to put it into meters. We know that it's the third order maximum, so m is just simply 3. We sub it into our formula, the path difference is equal to m lambda, so 0.12 is equal to 3 lambda, and then rearrange it to get lambda is equal to 0.04 meters. Okay, as I said, I am going to film another shorter video just kind of going over visually how you can kind of work out that the path difference is 1 lambda when they're at the first order maximum, and how we can work out that the path difference is a half lambda at the first order minimum and stuff like that. So I will upload that as well. So this is the first part of interference. There is a second part, but I will upload that as a separate wee video. Okay, that's us for today.